Hi budding engineers, welcome to Section-Shear lectures and welcome to the new playlist on the advanced steel designs. In today's class, we shall see the combined trapezoidal grillage foundation as per the limit state designs conforming to IS 800-2007. In the previous class, we have seen the combined rectangular grillage foundation as per the same limit state method IS 800-2007 itself. I hope you enjoyed the discussions there. Then try to support our channel by clicking like, share, subscribe and comment our YouTube channel, right? Now, before we see the actual discussion, let us move to the brief discussion of the brief profile of the speaker. I, that is Dr. D. Rupesh Kumar. I obtained my BTech in Civil Engineering from Nagarjuna University in 1994, MTech Section Engineering from JNTU Hyderabad in 2000, PhD Section Engineering from JNTU Hyderabad in 2009. Presently, I am working as Professor of Department of Civil Engineering, University College of Engineering, Usman University, Hyderabad, Telangana State. Right? I have an experience of 28 years, of which 7 years is in industry and 21 years is in teaching, teaching and research at graduate and postgraduate levels. My research areas include reinforced cement concrete design, structural steel design, structural analysis, point element analysis, earthquake engineering, bridge engineering, structural optimization. I published 45 research papers in international as well as national journals and conferences, and organized 3 international conferences and 11 national conferences and workshops, and attended 43 workshops, visited 2 countries, delivered 14 guest lectures, edited 3 books, supervising 14 PhD scholars and supervised 30 ME theses. I am actively involved in various consultancy works that are offered by the Department of Civil Engineering and completed over 800 plus design proof checks and 150 plus designs of the RCC, steel, composite, low-rise, high-rise, multi-story buildings and road as well as rail bridges. Right now, however, now let us move to the discussion, student. Right, we wish to do the designs of a combined trapezoidal grillage foundation, which I have already discussed in the previous videos, ASD1 as well as ASD3, right? How to design these, how to proportion these, I have already discussed that elaborately. However, I am just recapitulating that, right, for your information, right? This the design of a trapezoidal grillage foundation shall be done, right, when it is subjected to loading P1 and P2 on the 2 columns transferred through the base plate, right? However, now the assumption is that if P1 is greater than P2, then obviously the width required at that side is more. L1 is greater than L2 because load P2 is smaller than that of the P1, right? And the length of this grillage foundation is equal to B, right? Therefore, with these notations, right, or let me show the notations like this further, right? These notations we have used, right? This is how a combined grillage foundation. The notations are like this: that load P is transferred over a base plate of size L1 by B1, and load P2 on the right column is transferred on a base plate of size L2 by B2, and the center distance between the columns is equal to small c, and the distance from the center line of the column to the left is A1, and similarly the distance from the center line of the right column to the end of the beam is A2, whereas A1 prime and A2 primes are the net cantilever projections to the left and to the right of the base plates, right? This is A1 prime and this is A2 prime, and let B is the width of the foundation, and just now shown that let L1 and L2 be the lengths at the left as well as the right ends respectively. With these notations, then I can say that what is the area? Area is equal to L1 plus L2 divided by 2 average length multiplied by breadth. However, we have A by B from this is equal to L1 plus L2 by 2. Whereas if I take the left end of the grillage, end of the beam as a reference, this as a reference, right? Then by taking that as a reference, now I'll find out where the CG of these loads is located, right? That is how x bar is equal to L1 plus 2 L2 divided by L1 plus L2 multiplied by B by 3 using this CG formula for the trapezoidal loads, right? Therefore, upon substitution, it now works out say V by 3 multiplied by 1 plus L2 divided by L1 plus L2, or it is also numerically equal to, right? By taking the left hand side as a reference, now I can say that CG of these two loads is P1 multiplied by A1 plus P2 multiplied by A1 plus C. This distance is equal to C, that divided by total load P, which is summation of P1 plus P2. Both are the same equations representing the CG x bar. However, now I'll say that now I want to get what is the distance between these D. Now let me show this figure, right? Therefore, let D be the distance between this B by 2 and this x1 bar, right? Therefore, that distance I am finding out as given by this, right? D is equal to B by 2 minus x bar is equal to B by 2 minus x bar is already known from the above equation. If I substitute that, B by 3 multiplied by 1 plus L2 divided by L1 plus L2. However, rearranging the term by taking this B by 6 common and taking to the other side, now the above equation will become 6D divided by B is equal to 1 minus 2 L2 divided by L1 plus L2, or it is L1 minus L2 divided by L1 plus L2. However, multiplying on both sides by A by B, now I'll get 6D A by B is equal to A by B multiplied by L1 minus L2 divided by L1 plus L2. However, A is nothing but L1 plus L2 divided by 2 multiplied by B. Therefore, B gets cancelled, leaving L1 minus L2 divided by L1 plus L2 multiplied by L1 plus L2 divided by 2. However, solving these, this equation 1, right, as well as this equation 2, now I'll get say L1 is equal to A by B plus 6 AD divided by B square, and L2 is equal to A divided by B minus 6 AD divided by B square. Therefore, that is how I'll be proportioning the trapezoidal grillage foundation. Therefore, now I've fixed the dimension L1 and L2. Now, then I know how to get that area. A required is equal to 1.1 multiplied by total load P1 plus P2 divided by Q, and the breadth required is equal to A1 plus A2 plus C, right? That is required. We will provide that much only, right? And x1 bar by taking the left hand column as a reference, then I'll get the CG as x bar is equal to P2 multiplied by C divided by P. I've changed my assumption, right? Therefore, now you can say x is equal to previously the reference was the left end, this end, for finding out the CG, right? Therefore, using that, now I can say that x bar is equal to x1 bar plus A1 also, right? Now, where x bar is equal to P1 A1 plus P2 multiplied by A1 plus C divided by P, that just now we have seen, right? Now, that is how the proportioning will be done, student, right? Then once the proportioning is done like this, therefore I have fixed the dimensions B and L1 and L2, and what is this A1 and A2, right? Sometimes the restrictions may be there for A1 and A2, that we need to see. And this is the net cantilever projection A1 double prime, and from the left end of the grillage to the top of the end of the second base A2 double prime, where A2 is from from the center of the column to the right end, right? And this is x bar from a left reference x bar. Remaining distance is B minus x bar, because this entire width is equal to B, right? And D is this distance, just now we have calculated, right? Now, then I'll go for the analysis, wherein if I consider the section 11 below the base plate, left hand base plate, then I'll get M1x, right? M1x is Q0 x squared divided by 2 multiplied by L1 minus x by 3 minus L1 minus L2 by B minus P1 by B1 x minus A1 prime multiplied by x minus A1 prime whole square by 2, right? Actually, that is whole square by 2, right? Similarly, if I take a section between this point 1 to 2, right? Therefore, in middle part, now I'll get the bending moment given by this m12x is given by q0 x square divided by 2 multiplied by L1 minus x by 3 multiplied by L1 minus L2 divided by b minus p1 x minus a1, right? Similarly, L2x means just beyond this, right? Below this base plate, below this second base plate, it is given by this m2x is equal to q0 x square divided by 2 multiplied by L1 minus x by 3 L1 minus L2 by b minus p1 x minus a minus p2 by b2. Please make a note, because just below that even p2 will also come into picture, right? The intensity of the load below this one is p2 divided by b2, students, right? Therefore, that multiplied by x minus a2 double prime multiplied by x minus a2 double prime by 2. That works out x minus a2 double prime whole square divided by 2, right? Where a2 prime is, if I notate that as a1 plus c, that already shown in the schematic, right? Therefore, that is how this is here to here is a2 double prime, right? And now also we can write the equations for the shear forces also. Therefore, just below that first concentrated load, right? V1x is given by n is q0 x multiplied by L1 minus x by 3 minus L1 minus L2 divided by b minus p1 by b x minus a1 prime, or even differentiating these m1x, m12x, m2x, I'll get the corresponding shear forces in those zones. By equating those shear forces equal to 0, I'll get some x starting from the left reference or from the right reference. Now we are considered from the left reference. By substituting back into these three equations, I'll get the bending moment, maximum bending moment in those zones. The negative, maximum negative bending moment, maximum positive bending moment, and maximum negative bending moment on the right hand side, RHS side, right? That is how the analysis should be done. I just recapitulated these what we have discussed in the ASD1 and ASD3 videos. Now let us move quickly to that of a design problem, student, right? I hope you understood how the proportioning as well as analysis should be done, right? Now this is a numeric problem wherein two columns having sections ISHB 450 at the rate of 92.5 kg per meter and ISHB 400 at the rate of 82.2 kg per meter carry axial loads of these are the factor loads, students, right, of 2500 kilonewton as well as 2000 kilonewton respectively, and are spaced 3.5 meter apart, center to center. The size of the base plate under each of the column is 800 by 800 mm, right? The available space to the side of the column 1 is 1200 mm, and up to the center of the column, and to that of the side of the column 2 is 1500 mm up to the column center. These are the restrictions given. By taking the safe bearing capacity as a 200 kilonewton per meter square, now design a suitable combined grillage foundation. Suitable combined grillage foundation, right? That is how the data is given, student, right? However, there are the restrictions given. Only 1200 mm is available to the left of the first column and 1500 mm available to the right of the column. Therefore, keeping in view this restriction, right, we may design this as a combined trapezoidal grillage foundation, right? Combined trapezoidal grillage foundation. Even from loads point of view, the loads 2500 and 2000 are almost heavy loads, right? Therefore, even there also I may require a trapezoidal grillage foundation only to optimize the section. Therefore, now I'll proceed with this optimized section. I want to optimize the section. Therefore, I'll proceed with the trapezoidal grillage foundation only, right? Now, and also regarding the steel sections, there is no data given. Therefore, what I am assuming, that assume Fe410 grade steel, where ultimate strength of the steel is equal to Fu is equal to 410 megapascals Newton per mm square, and yield stress of this steel is equal to 250 megapascal, right? And even if I go to IS 800 2007 table 5, page number 30, let me go to that page number 30, student, right? Just wait for a moment. Page number 30. Yes, This is the page number 30, table 5. Here the resistance governed by the yielding gamma m0 is equal to 1.1, and resistance governed by the buckling gamma m0 is also 1.1, whereas resistance governed by the ultimate stress gamma m1 is equal to 1.25. Therefore, I have recalled this data for the partial safety factors also. Now what I'll do is I'll do the very first step, the proportioning of the footings. First step is the proportion of the footings, right? Therefore, just now explained how the proportioning should be done. However, now because of the availability of the lesser space to the left side of the column 1, and slightly more space to the right side column 2, will proceed with the design of a combined trapezoidal grillage foundation like this, right? Now let me show this, student, right? What now I'm showing is a combined grillage foundation, right? Or let me go to this schematic, right? This is a combined grillage foundation, wherein here more load is there just below that first load. Therefore, I have more L1 compared to that of the less load under that second column. Therefore, less L2. This is what a combined trapezoidal grillage foundation I'll be designing, right? Now let us do the proportioning. Then now I am noting down that data. Now I do have this A1 is equal to 1200 mm already given in the problem. A restriction is there, and A2 is 1500 mm, 1.5 meter, and now I do have B, the width of this footing from these, and also C, the center distance between the columns is given as 3.5 meter. That is also given. This data I have noted down, and Q is given as, the SBC is given as 200 kN per meter square. And L1 by B1 is equal to L2 by B2 is 800 mm by 800 mm. This is the data given, student. Therefore, from this now I'll say what is the width of the footing is nothing but A1 plus A2 plus C, substituting which now I'll get say a value 1.2 plus 1.5 plus 3.5. It works out say 6.2 meter, and the distance x1 bar of the CG of the loads from P1 load. Please make a note, I am taking a reference as the P1, right? This point, the central end of this column, right? Not the left end of this grillage, bottom grillage. I am taking the central end of the, or let me see, right, like this, right? From this central line, I am not going with respect to the left, right? Therefore, with respect to the central line of this first column, I am finding out that as x1 bar as per the notation, P2 multiplied by C divided by total load. Therefore, now I do have P2 is 2000 multiplied by C, center to center distance is 3.5 meter divided by total load is equal to 2500 plus 2000. That works out say 4500 in the denominator, or it is x1 bar is equal to 1.556 meters. But please make a note that these are the already factored loads, right? In the numerator also I do have the factored load, in the denominator also factored load. Therefore, actually it should be done with unfactored loads. Therefore, the numerator and denominator both I am multiplying with 1.5 which get cancelled, which will not affect the finding out the CG value. Please make a note of this, students, right? Then here the CG distance between the distance of the CG of the loads from the larger width is x bar, that is equal to A1 plus x1 bar. However, A1 is already given the problem as 1.2 is the maximum restriction, and that itself we are using, plus 1.556. It now works out say 2.756 is the distance from this left end, right? Left end of this grillage up to the CG is equal to 2.756, right? Now, and also the distance between the CG of the loads and center of the footing, right? This is actually the eccentricity, right? Exactly the eccentricity. Therefore, D is equal to B by 2 minus x bar is equal to say 3.1 minus 2.756. 0.344 is the eccentricity, right? Right? Therefore, now we would have this much of eccentricity, right? As already shown in the previous figure like this, right? This much of eccentricity is there, D, or eccentricity, right? Therefore, now that is also calculated. Therefore, Now I'll calculate what is the required base area. Air equal is equal to 1.1 multiplied by P1 plus P2 divided by Q, where this 1.1 is the additional load considered for the self weight in terms of the applied loads P1 and P2, in terms of applied load P1 and P2, right? 10% more. Therefore, if I do using this, now I'll get 1.1 multiplied by 4,500 is a factor load, that divided by 1.5, right? 3000 divided by 200. 1.1 multiplied by 3000 divided by 200. It now works out. Say a value 16.5 square meters. 16.5 square meters. However, because the footing width is large, even the length required may also be large, right? Even let me see, I'm almost providing a length of L1 is equal to 5.33 and L2 is equal to 2.67. Therefore, lengths are also large. Therefore, this self weight, just 10% increment, may not be exactly true. Now let me check, right? If it is not so, then I'll modify the area required. Therefore, now I'm doing the calculation with these assumptions that L1 is equal to 5.33 and L2 is equal to 2.67. Though I have not calculated, I am just illustrating this, right? Therefore, what is the self weight? What is the self weight of the footing? Therefore, the average length, actually this is that of the end of the grillage foundation to the end of the grillage foundation only, right? 5.33 plus 2.67, that divided by 2, average length of the grillage itself is 4 meter, right? Therefore, now self weight is nothing but this 6.2 meter width multiplied by average length 4 meter. However, I am assuming to provide the beams of 550 mm depth. Therefore, over that, even 100 mm is the minimum clearance cover required. Therefore, the depth of that concrete is equal to 750 mm, right? Plus, then for the base plates, just below the base plate, I want to provide like a pedestal of 1 meter by 1 meter, because the size of the base plate given is 800 mm by 800 mm. Therefore, I want to provide 1 meter by 1 meter. There are two such pedestals, right? Wherein in the top tier grillage, I want to provide say 200 mm depth beams. Therefore, 200 plus 100 mm, that works out say 300 mm. There are two such pedestals. Therefore, what is the self weight of this concrete? That multiplied by 25 kilonewton per meter cube, right? Plus that of the soil overburden pressure over that is equal to 6.2 multiplied by 4.2, that multiplied by this is the intensity of the pressure. I'm sorry, 6.2 multiplied by 4.4, 6.2 multiplied by 4 is the total area of the base plate, that of the foundation, from which I will deduct that of these two pedestals, right? 2 multiplied by 1 meter, right? 2 meter square. Therefore, now I'll get so many meter square. Whereas now, if I assume the soil overburden over that as 0.3, therefore that multiplied by 0.3, this multiplied by 0.3, therefore that multiplied by intensity of the soil is equal to 19, therefore that multiplied by 19 kilonewton per meter cube. If I do that, now I'll get approximately 913.2 kilonewton, or approximately 920 kilonewton. Therefore, this 920 kilonewton as compared to that of the previous value 3000, 10% means just 300. Therefore, this 920 is much greater than that of the 10% more. Therefore, now what I'll do is I'll calculate with exact calculation, right? Exact calculation as say like this, that this 2500 plus 2000 are the factor loads, that divided by 1.5 means 3000 plus 920 unfactored load. unfactored load, that divided by SBC 200. Therefore now I require 19.6 meter square area required by taking the self-weight of the footing as well as the soil overburden pressure over the footing also. Therefore, without considering that soil overburden pressure and exact calculation of the self-weight, I was getting only just 16.5 meter square, but by exact refined calculation I am getting 19.6. Therefore now what I'll say is not less than 19.6, but I am proceeding with a area of 24.75 meter square. Even I am providing more, right? I want to provide more, right? Therefore by taking this area, what I want to provide is 24.75. What is the length required now? L1. Therefore that is given by L1 is equal to A by B plus 6AD divided by B square, substituting the numeric values now. Now I do have A is equal to 24.75. Actually I require 19.6, but I want to provide 24.75. Therefore 24.75 divided by 6.2. B is already fixed, plus 6 multiplied by 24.75 multiplied by that eccentricity D, right? 0.344 divided by 6.2 whole square. It now works out, say, a value 5.321, right? Whereas if I calculate this with exact 19.6, what is that value, right? Therefore if I calculate using this exact value of 19.6, I am getting this value as 4.21, whereas if I want to provide 24.75, I am getting a value of 321, right? Like that the length required at the other end, L2 is equal to A by B minus 6AD divided by B square. That now works out, say, 2.663 or is approximately 2.67 by taking 24.75 meter square as the area required. However, if I take that area required as 19.6 meter square, I require 9.11. Therefore what now I am doing is I am proceeding with this area 24.75 and I am fixing this length L1 as 5.33 and length L2 as 2.67. That is how I have just done the proportioning, as L1 is equal to 5.33 meter student and as well as L2 is equal to 2.67, so that the SBC will be within permissible limit, right? If I exactly provide 19.6, then the SBC will be exceeded due to overburden pressures. Therefore I don't want to do that. Hence the actual CG X bar is equal to B by 3 multiplied by 1 plus L2 divided by L1 plus L2 upon substitution. Now I'll get 2.7564, which is almost near to that of our calculated value. X bar is equal to 2.756 we got, right? However, now I'm having the same value. Therefore it is very near to our X bar what we found, and now these are the results of the proportioning, that B is equal to 6.2 meter and L1 is equal to 5.33 and L2 is equal to 2.67 meter and C is equal to 3.5 meter, and A1 already given the problem as 1.2 meter and A2 is equal to 1.5 meter. Therefore what is A1 prime net cantilever projection is equal to A1 minus V1 by 2. Therefore that is 1.2 minus 0.8 by 2 means 1.2 minus 0.4, it is equal to 0.8 meter. Similarly A2 prime is nothing but A2 minus B2 divided by 2. It works out as 1.5 minus 0.4, 1.1 meter. Similarly A2 prime is nothing but B minus A2 minus B2 by 2. It is 6.2 minus 1.5 minus 0.4. It works out as 4.3 meters. As per these notations what I have shown in this figure, right? As per all these notations I just fixed the dimensions. Proportioning is now over. All the dimensions are just now fixed, right? Each and every dimension are fixed, right? Once the proportioning is over, now what I'll do, I'll go for the analysis of the top tier as well as the bottom tiers, right? Now let us see the first analysis of the top tier beams, top tier beams under the first column, left column, under the load P1. Therefore, now the length of the beam under P1 is equal to L2 plus L1 minus L2 multiplied by C plus A2 by B, right? Therefore, now I do have this. Upon substitution, it works out, say 2.67 plus 5.33 minus 2.67 multiplied by 3.5 plus 1.5 divided by 6.2. It works out, say y1 or y1 is equal to 4.815 meters. Therefore, now the length of the central beam, length of this central beam is equal to 4.815. Length of the central beam is equal to 4.815, right? Now, whereas the base plate dimension L1 by B1 both are 0.8 meters respectively. Therefore, what is the maximum bending moment? I already shown in the ASD1 video this analysis, right? Even in today also I have just elaborately explained. I'll get maximum bending moment P1 by 8 multiplied by Y1 minus L1, right? Therefore, upon substitution, 2500 divided by 8 multiplied by 4.815 minus 0.8. Just now I obtained this Y1. Therefore, it works out, say 1254.7 kilonewton meter. Whereas I am already having this factor load of 2500. This is the factor load which is already given in the problem. It is given that these are the factor loads, right? Factor loads, right? Therefore, now I'll go for the design. Once I have obtained the maximum bending moment, now analysis under the beam, under the load P1, left column P1 is over. Now I'll go for the section modulus required, right? Now, for which I need to go to this IS 800 2007 class 8.2.1.2 page number 53. Page number 53. Let me go to this page number 53, students, at a quicker pace of IS 800 2007 53, right? Yes, 53. I do have this, right? Now the code says that if d by t is less than or equal to 67 times epsilon, then 1, right? And also then in such a case the shear buckling of the beam will not happen. Shear buckling of the beam will not happen as per the class 8.2.1.1, as well as if the design shear force does not exceed 0.6 VD. 0.6 VD means low shear. As per this class 8.2.1.2 low shear, then MD is given by beta B ZP Fi divided by gamma m naught, where MD shall be less than 1.2 ZE Fi divided by gamma m naught in case of simply supported beam, or 1.5 ZE Fi divided by gamma m naught in case of the cantilever beams, where beta B is equal to 1 for plastic and compact section, and beta B is the ratio of the elastic to plastic section modulus for semi-compact sections, right? However, if V is greater than 0.6 VD, 0.6 VD, then MD is equal to MDV. By taking care of this high shear, we need to reduce the design capacity of the beam. However, now to start with, I have assumed this. Therefore, two assumptions. The assumptions are that assuming plastic section as well as the low shear. To start with, I am assuming so. Therefore, the section modulus required ZP req is equal to M divided by Fi divided by gamma m naught upon substitution. 1254.7 10 to the power 6 multiplied by 1.1 divided by 250. It works out same 5520 into 10 to the power 3 mm cube. However, please see that in the top tier hardly we can provide, say, 3 or 4 beams only, because the space available under the base plate is not too large. Hardly it is 800 mm available. Therefore, under that I can provide not more than, say, 3 or 4 beams only, as I am illustrating here, right? That is a 1, 2, 3 or 4 at maximum. Whereas in the lower tier I can provide more number of beams, because that is over a length L1 to L2, right? Here only over a width of base plate only. Therefore, within that hardly I can provide 3 or 4, at maximum 4 only, not more. Therefore, I am assuming 3 beams. Then what is the section modulus required for each of that beam is equal to 5520 divided by 3. That works out, say, 1840 into 10 to the power 3 mm cube. However, for trial section, I'll increase this value by 20%. Therefore, 1.2 multiplied by 1840 10 to the power 3. It works out, say, 2208 10 to the power 3 mm cube, right? Therefore, now what I'll do is I'll go to IS 800. 2007, table 46, page number 139, and alternatively from SP61 1964, table 1, page number 2. Either of the two is true, right? Now let me go to this IS 800, IS 800, page number 139, students, right? Page number 139, yes, 139. And then in that page, wherein how much section modulus required is, I shall try with the 2208 centimeter cube. Therefore, what now I'm doing is I'm assuming ISLB 550 at a rate of 86.3 kg per meter, which is furnishing a plastic section modulus of 2228.16 centimeter cube. Let me check this. ISLB 550, right? Sorry, not this one, right? ISLB 550, right? Therefore, I do have this ISLB 550, not this one. Yeah, this one, right? ISLB 550 at the rate of 86.3 kg per meter, which is furnishing a section modulus of 2228.16. 2228.16. Therefore, once it is okay, then I'll note down the other relevant property, students, like this, right? What is the depth of the section 550 and width of the flange? Width of the flange is equal to BF is equal to 190 and depth is equal to 550, and the thickness of the flange 15 mm and the thickness of the web is equal to 9.9 mm. Right? Even I'll note down the elastic section modulus Z is equal to 1933.2 centimeter cube. Right? Whereas even I can go to this SP61, wherein ISLB 550 is also seen here, right? ISLB 550 at a rate of 86.3. The same properties can also be noted down here, but here you cannot find the plastic section modulus ZP from ISI handbook for structural engineers, which is called SP61 1964. Therefore, for which I need to refer once again to IS 800 2007. I have noted down all the relevant properties, students. Therefore, once I note down these properties, then I'll say that whether the section modulus required provided is it greater than that required. However, I need to provide 2208 centimeter cube, but this section is furnishing 2228.16 centimeter cube. Therefore, it is okay. This is okay. Once this is okay, I've just noted down the other relevant properties. Just now I did told. These are the other relevant properties which I have noted down. Z is equal to 1933.2 centimeter cube. H is equal to 550. BF is equal to 190 mm. TW is equal to 9.9 mm, and H2 is equal to 36.95 mm, and H1 is equal to 476.1. What is H1 is pure vertical part of this web, excluding the thickness of the flange as well as the root radius at the top as well as at the bottom, right? And thickness of the flange is equal to 15 mm. And once I note down these properties, student, then I'll make the different checks. What are the different checks? The first check is that the check for the clearance between the ends of the webs. Check for the clearance between the ends of the webs, right? Therefore, the check for the clear spacing between the flanges is equal to, right? Yes, I do have 800 mm width of this base plate, and what is the width of this flange is equal to 190 mm. There are 1, 2, 3. Therefore, between that only 2 spacings will be there, right? Therefore, what is that? Like this, right? I do have 800 mm. I am just taking a cut section 800 mm. I am providing 3. Therefore, what is this clear spacing? Right? Between 3, only 2 spacings will be there. Therefore, this spacing is equal to 115 mm, which is greater than 75 mm. Therefore, it is okay. First check is okay, right? Now, the second check is the check for the shear. However, now I'll analyze what is the maximum shear force, student, right? Given by this formula, P1 divided by 2y1 multiplied by y1 minus L1, which is resisted by n number of beams, where n is equal to now 3 beams. Therefore, if I substitute numeric values, I'll get the maximum factored shear force, because this 2500 is already factored load divided by 2 multiplied by 4.815, which is shared by 3 beams. That multiplied by 4.815 minus 0.8, it works out say 347.44 kilonewton, right? once I have this factored design shear force, then I'll find out as per this class 800 2007 class 8.4 page number 59. Let me go to this page number 59, student, of IS 800, page number 59. 59. Yes, this is that page number 59, where it gives the factor design shear force V should be less than or equal to VD, where VD is the design strength given by Vn divided by gamma m naught, where Vn is equal to Vp, Vp is equal to AV multiplied by Fy W divided by root 3, where AV is the shear area. For I and channel sections, about the major axis of the bending, for hot rolled section, AV is nothing but H multiplied by TW, right? This height of this web multiplied by thickness of this web, right? Therefore, now I'll substitute these into this formula, therefore, which gives the design shear strength of the section as, say, depth, sorry, AV is equal to depth multiplied by thickness of the web, 550 multiplied by 9.9 multiplied by 250 divided by root 3 divided by 1.1, that divided by 10 to the power 3, so that I'll get in terms of kilonewtons, which is 714.4 kilonewtons, right? However, this is the design shear strength. However, the factored shear force is just 347.4 kilonewton, which is much less than the design shear strength or design shear capacity of the assumed ISMB, ISLB 550 section, right? Therefore, it is okay in shear check. It is also okay in shear check. And let us also check the third check as the check for high shear, right? As per IS 800 2007 class 8.2.1.2, page number 53. I already told that if let me go to this page number 53, students, right? 53, not this one, right? 53, yes, right, this one, right? If the design shear does not exceed 0.6 VD, then that is called the low shear. Whether this is low shear or high shear, I am checking. Therefore, now what I am doing is here 0.6 multiplied by VD. However, VD is equal to just to be obtained as 714.4. That multiplied by 60% means 428.64 kilonewton. However, my factored shear is 347, is much less than this 428.64. Therefore, it is a case of low shear, means the design moment capacity MD is MD, not MDV, is the conclusion. Therefore, it is a low shear. Therefore, MD is equal to MD only, not MDV, right? That is the third check, right? Now, I'll go for the fourth check, which is the check for the moment capacity, right? I'll find out how much each of these section can resist as per this as per the IS 800. However, before that I need to do the section classification. Therefore, this section classification will be done as per the table 2 of IS 800, page number 18. As per the page number 18, whereas for rolled steel section B by TF, now I do have this width of the flange as 190. Therefore, the outstanding leg is 190 by 2. Therefore, this is outstanding leg, which is 95 mm divided by thickness of the flange 15. Therefore, this ratio will work out 6.33. However, as per this page number 18, it should be less than or equal to 9.4 times epsilon, where epsilon is equal to square root of 250 divided by Fy. In our case, Fy itself is 1. Therefore, epsilon is a stress ratio is equal to 1. And also D divided by TW. However, D is H1 is equal to 476.09 divided by thickness of the web is equal to 48.09, which is less than 84. Therefore, as per this table 18, let me just go to this 18 table 2, page number 18. 18, right? Then that is, yes. Therefore, the outstanding element of a compression flange as per this table 2 of IS 800 2007 for rolled steel section B by TF, if it is less than 9.4 times epsilon, then the section is class 1 or plastic section, right? Or otherwise, if it is greater than 9.4 and less than 10.5 times epsilon, then that is a compact section. And if it is greater than 10.5 and less than 15.7 times epsilon, then there is a semi-compact section. Similarly, for web of an I or H section, right? If neutral axis is at the mid depth, for in our case, that is a case because it is symmetric about the horizontal axis. Therefore, d by tw, if it is less than or equal to 84 times epsilon, then the section is plastic section. Or if it is greater than 84 times epsilon and less than 105, then that is a compact section. And if it is greater than 101 epsilon and less than 126 epsilon, then that is a semi-compact section. However, we got both the checks. It is right, which was less than 9 for the flange. It was less than 9.4 times epsilon, right, like this, right? And also for the web, it is less than 84 because we got 48.09, which is less than 84. Therefore, both the web as well as the flange have plastified. Therefore, the section is a plastic section. Therefore, beta is equal to 1. As per this IS 800, beta is equal to 1. Therefore, now what I'll do is that I'll calculate the design bending strength as per this class 8.2.1.2, right? Therefore, that now works out, say MD is equal to beta B for the plastic section is equal to 1. Therefore, now if I substitute beta B is equal to 1 multiplied by ZP is equal to 2228 into 10 to the power 3, Fi is equal to 250 divided by 1.1. However, this value should be less than or equal to 1.2 multiplied by ZE. Elastic section modulus is equal to 1933 into 10 to the power 3 multiplied by Fi 250 divided by 1.1. Therefore, both of these results will now work out. The first value is equal to 506.6 10 to the power 6 kilonewton mm, right? Should be less than or equal to 527.18 into 10 to the power 6 Newton mm. However, this 506.6 is less than 527.18. Therefore, it is okay. Let us say if you get this result as say 566.6, it should be less than or equal to 527. Then you restrict this value to 527 only. Therefore, we are getting this as okay. Therefore, I will take the design bending strength or design bending capacity as 506. However, each of the beam is subjected to a factored bending moment of 1254 divided by 3, 418 kilonewton only, whereas each of the section can resist up to 506.6, right? Therefore, it is okay. Hence, it is okay in flexure criteria. It was also okay in shear criteria. It is now okay in the flexure criteria, second one, right? Therefore, the fourth check is also over. Now, is it okay in buckling and crippling criteria also, right? Buckling and crippling, there is a buckling criteria as well as crippling criteria, right? Crippling criteria, right? If this is okay, then we'll assume this as the final section. Therefore, now what I'll do is I'll go for the check for the crippling, right? Now, as per this IS 800 2007 class 8.7.4 page number 67. Let me go to this page number 67 of IS 800, right? 67. Yes, this is that page number 67, student, wherein I have to have check for crippling, right? Bearing stiffness, right? The bearing strength of the web FW is B1 plus N2 multiplied by thickness of the web multiplied by FYW divided by gamma m naught, where B1 is the stiff bearing length and N2 is the length obtained by dispersion through the flange to the web junction at a slope of 1:2.5 to the plane of the flange. Now I'll show that schematically like this, right? This is how when web is buckling, right? Right now, this is web buckling actually. This is web buckling. This check we'll do later, right? This is what web buckling, right, at the neutral axis. However, this is web buckling. Now we are doing this web crippling. Therefore, a local kink will form at the intersection of the flange with the web. This is what called a crippling, right? Infinite rotation will occur at the intersection of the flange with the web if at all a concentrated load is put, whereas at the supports, right, at the intersection of the flange with the web at the bottom will happen, right? That that flange will undergo infinite rotation, right? That is called the web crippling. Therefore, that will happen over a slope of 1:2.5 up to the end of the root radius, up to the end of the root radius. Therefore, now we'll consider thickness of the flange plus root radius, right? That multiplied by 2.5. If at all it is dispersing over one direction only. If at all a concentrated load is there, then 2 n2 plus n2, that is how the width of the dispersion, b1 plus n2 plus n2, right? Therefore, however, in our present case, what we are assuming is like this, right? Like this, student, right? Therefore, I do have the base plate over this base plate, right? The load will disperse on either side. Therefore, n2 plus n2, where b is equal to width of this base plate 800 mm plus n2 plus n2, that I need to calculate, so that whether a crippling will occur at the intersection of this flange with the web or not, that I'll make a check for one beam section, right? Then these properties we already noted down, student, right? Therefore, what now I'll do is that bearing width is nothing but just now already shown in the figure 800 mm, because that width of the base plate is equal to 800 mm, right? Therefore, what is n2? Because it is dispersing on two sides, 2 multiplied by 2.5 multiplied by this H2. Therefore, substituting these numeric values, 2 multiplied by 2.5 multiplied by H2. H2 is already noted down, 36.95. It works out, say, 184.75. Therefore, the strength of the web against web crippling, FW, upon substitution, B1 is 800 plus this N2 is equal to 184 multiplied by thickness of the web, 9.9 multiplied by 250 divided by 1.1 divided by 10 to the power 3. It now works out, say 2215.7 kilonewton for each of the beam, whereas each of the beam is subjected to a factored shear force of just 347.4 kilonewton only. Therefore, it is okay in web crippling criteria. This fourth check is also over, right? If this is okay, then I need to do this web buckling check also, whether web will buckle or not. Therefore, check for the last check is the fifth check. Check for web buckling as per IS 800 2007 class 8.7.3.1 page number 67. Or before that, let me also check this class 8.2.1.1 page number 53. Just now we already seen. Let me go to this page number 53, student. Page number 53. S53, right? And then in that page number 53, if d by t is less than or equal to 67 times epsilon, then the check for buckling in web need not be done, right? That is what the code says, right? As per this class 8.2.1 for laterally supported beams, right? Whereas these are already laterally supported beams because they are encased beams. What we are now discussing are encased beams. Obviously, the buckling, neither buckling will happen nor the crippling will happen because the concrete, the sections are already embedded in the concrete. They are already this check need not be done, but nevertheless we'll assume that if at all the concrete has already failed or it lost the bond, if at all it is losing the bond, then this check will come into picture. Otherwise, if there is no loss of the bond between the concrete and the section, then if that bond is ensured, then these checks need not be done. However, assuming that this bond will be lost over a period of time, I am making a check. Whether the buckling will happen or not, right? Whether it will fail in buckling criteria or not. Therefore, however, now let me see this d by tw. Just now we got 48.09. in a section classification which is much less than 67, right? This section classification we have seen like this right here, right? This was 48.09, therefore that was much less than 67. Therefore we can say that the buckling will not happen, or the web will not buckle under this shear force, right? And the web buckling check need not be done. However, if it is required, how it need to be done? Therefore, if it is required, then it must be done as per the class 8.7.3.1, page number 67. Let me go to this page number 67, so that I'll illustrate, right? Not this one, 67. Yes, right? Therefore, this is how that 67 web check, right? Now, the effective length of the web for evaluating the slenderness ratio shall be calculated as per this 8.7.1.5. I'll come to that. The area of the cross section shall be taken as B1 plus N1 multiplied by TW, where B1 is the width of the strip bearing on the flange, as per this class 8.7.1.2, and N1 is the dispersion of the load through web at 45 degree to the level of the half the depth of the cross section. Let me also go to this 8.7.1.5, right? This one, right? This is what at a dispersion of 45 degree, student, as per this figure 15, right? And also, what is the effective length shall be taken as 0.7 times the length, right? Therefore, KL is equal to 0.7 L per flange, which is restrained against the rotation in the plane of the stiffener. Therefore, using these Codal specifications, now what I'll do is that I want to calculate the slenderness ratio. Therefore, for which what now I'll do is that slenderness ratio is the effective length by R minimum radius of gyration. Therefore, effective length is equal to 0.7 L divided by radius of gyration. By taking this width of the dispersion as B, and its thickness is equal to therefore the radius of gyration is nothing but square root of I divided by A. Therefore, I is BT cubed by 12 divided by area is equal to B multiplied by thickness. Therefore, if I take this ratio under square root, now what I'll have is the minimum radius of gyration is T divided by root 12. Right? Therefore, that now works out T divided by 2 multiplied by root 3. Therefore, if I substitute back these in this formula, now I'll get this slenderness ratio lambda is equal to 0.7 L divided by T divided by root 12. Therefore, that now works out say a value 2.42 multiplied by H1 divided by thickness of the web. Therefore, R say approximately 2.5. I am saying approximately slenderness ratio is 2.5 multiplied by H1 divided by thickness of the web. Therefore, substituting the numeric values, the slenderness ratio 2.5 multiplied by 476.1 divided by 9.9, right? 9.9, which is equal to 120.2. Let me show this schematic, student, right? Let me go to this, not this one, right? This schematic, not this one, right? This is what I am trying to do, right? I am trying to find the slenderness ratio over this 0.7 L, right? However, the web is presumed to be effectively restrained between this top flange and bottom flange. Therefore, the effective length is equal to 0.7. Now, like this, right? Therefore, buckling is happening, right? Under the concentrated load N1. Therefore, B1 plus 2N1. Whereas just above this constant at the support, B1 plus N1 only. You please see this at a dispersion of 45 degree. Like this, right? At a dispersion of 45 degree. B1 plus N1 are below the concentrated load B1 plus N1 at the neutral axis. This much of width will be trying that multiplied by its thickness will be resisting the buckling at that neutral axis, right? That calculation we are doing now, right? I hope you understood what we are doing, right? Therefore, once I get this effective, this slenderness ratio, maximum slenderness ratio 120.2. Now, what I'll do is I go to this table 10 of IIC attended 2007, page number 44. Page number 44, wherein now I'll calculate. Let me go to this page 44. Just wait for a moment. Page number 44. Yes, I am there in page number 44. Therefore, not this one. Yes, buckling class of the cross section. Buckling class of the cross section. There, for this rolled steel section, if h by b f is greater than 1.1 and thickness of the flange is less than 40. However, in this case, our thickness of the flange is much less than 40. Therefore, I need to calculate if h by b is greater than 1.2, then about the major axis of the bending, means this horizontal axis, z axis, then there is a buckling class A. About this weak minor axis or weak axis, the buckling class is B. Therefore, let me check this, right? As per this table 10, page number this page number 44, right? Therefore, I am doing that calculation, student, right? Therefore, now I have h 550 is the depth of the intersection, that divided by width of the flange 190. It works out at 2.89, which is much greater than 1.2. Therefore, the buckling class of this rolled steel I-beam section ISLB 550 is A class, about the major axis of bending, ZZ axis. Therefore, once I fix the buckling class as A, then I'll go to page number 40, table 9A. Let me go to that page number 40, page number 40 of 9A. Yes, yes, I am there in page number 49A, 9A. Whereas now I do have the slenderness ratio is calculated as 120. Therefore, now what I'll do is, from that table, I'll note down for slenderness ratio lambda 120, the FCD value, permissible design compressive stress, is 101, and for lambda is equal to 130, it is 88.3. Therefore, now I'll interpolate for 120.2, it is how much? This is equal to 101 minus 101 minus 88.3 divided by 10 multiplied by 0.2. That now works out, say, 100.746 Newton per mm square, right? Therefore, for 120 and 130, I have noted these values. You please see, for Fi is equal to 250, 120 and 130, these are 101 and 88.3 Newton per mm square are the design compressive stress FCD for buckling class A. For Fi is equal to 250, right? Therefore, once I get this FCD, design compressive stress, then what I'll do is now what is the web buckling strength or resistance of that section is equal to FC multiplied by D multiplied by FC is equal to FCDW, notated by FCDW, capital FCDW, which is P1 plus N1 multiplied by thickness of the web multiplied by FC, right? This word is in as per this formula, right? Then, if I substitute, I have to have the width B 800 mm and the depth is 550 by 2, 550 by 2 as per this. Let me once again go to this side. This is 550 by 2 and this is 550 by 2, right? Because here the base plate is there of 800 mm, therefore it is dispersing over. This is overall depth is equal to 550, therefore up to the neutral axis, one is 550 by 2, it is dispersion of 45, 550 by 2. Therefore, 800 plus 500 mm is the width of the dispersion, that multiplied by thickness of the web. Therefore, upon substitution, that thickness of the web 9.9 multiplied by this permissible compressive stress 100.746 divided by 10 to the power 3. It now works out approximately 1346 kilonewton, which is much greater than the shear force, factored shear force to which it is subjected is just 347.4 kilonewton only. Therefore, the web will not buckle. However, this was already guaranteed by the previous check, that if D by TW is less than 67, this web buckling check need not be done as per the class 8.2.1.1 page number 53. But nevertheless, if at all it is required, how this buckling check should be done, we have illustrated that, right? Once it is okay in the final check, then I'll say that my assumed section IS3 ISLB 550 are the final sections for the top tier under the concentrated load P1 or under the left column, like this: 1 2 3 1 2 3. Now I'm showing 1 2 3 4 5 6, but this is just a schematic. Now you take 3 ISLB 550, depth is ISLB 550. Once I complete that, then similarly I try to analyze under the second column transmitting a load of P2, how many number of beams are required, right? Then I hope you understood this first part, right? Then I'll move to the second part, right, wherein I want to analyze and design the grillage under the concentrated load P2. Therefore, design of the upper tier beams under the concentrated load P2 or under the right column, right? Therefore, now the length of the beam under column transmitting a load of P2 is equal to Y2, notated by Y2 is equal to L2 plus, I need to interpolate because the length is varying over length of B from L1 to L2. Therefore, L2 is the base, smaller length, 2 plus L1 minus L2 at a rate of that divided by B. However, over at a length of A2 it is how much. Therefore, if I do that interpolation, now I'll get say Y2 is equal to 3.67 plus 5.33 minus 2.67 over length of 6.2. Therefore, over length of 1.5 it is how much. That now works out say 3.314 meters, right? Therefore, the length of the central beam is equal to 3.314 meter, and the length of the base plate small l2 is equal to small b2 is equal to 0.8 meter. Therefore, the maximum bending moment in this case also, the factored load P2 divided by 8 multiplied by Y2 minus L2, that factored load is equal to 2000 divided by 8 multiplied by 3.314 minus 0.8. It works out say 628.5 kilonewton meter is the maximum design moment. Means factored mu, right? Therefore, once even I'll get what is the shear force, even I'll analyze for getting the shear force also. Therefore, the maximum shear force under that second load is equal to P2 divided by 2 multiplied by Y2 multiplied by Y2 minus L2, which is shared by n number of beams. Therefore, if I substitute numeric values, now I'll get this V maximum is 2000 divided by 2 multiplied by 3.314 multiplied by 3, that whole multiplied by 3.314 minus 0.8. Therefore, it works out say 252.9 kilonewton. Once I do the analysis, now I'll proceed with the next subheading as the design. Therefore, now I'll initiate the designs. Therefore, in the first step, I am initiating the designs. I need to fix a section. Therefore, trial section. As per IS 800 2007, class 8.2.1.2, page number 53, just now explained in the previous subheadings that the total plastic section modulus required, right, is equal to the bending moment, right? ZP is equal to bending moment MD 628.5 divided by Fy divided by 1.1, means that divided by 250 divided by 1.1. That now works out say 2763.2 10 to power 3 mm cube. However, assuming 3 beams, the section modulus required for each of the beam is equal to 2763.2 divided by 3, or it works out say 921 10 to power 3 mm cube. Whereas for trial section will increase this by 20% more. Therefore, 1.2 multiplied by 921 10 to power 3. It works out say 1105.2 10 to power 3 mm cube. 1105. Therefore, now what I'll do is as per the table 46 of page number 139 of IS 800 2007, I'll try to fix. I'll try to choose a section ISLB 400 at a rate of 56.4. Let me go to the page 40. This page 139. Let me go to the page number 139, student, right? 139. Yes, ISLB. This section is IS. Not this one. IS. the section what I am trying to fix is ISLB 400 at 56, IS 56.9, ISLB 400, ISLB 400, not this one, this ISLB 400. Therefore, I'll note down the relevant properties for this ISLB 400 student, right? Not this one, yes. ISLB 400 at a rate of 56.9, for which the relevant properties are like this, right? The plastic section model is equal to 1099.45 and elastic section model is equal to 965.3, and other data that depth is equal to 400 and BF H is equal to 400 and BF is equal to 165 and thickness of the flange is equal to 12.5 and thickness of the web is equal to 8 mm, etc. Right? Once I note down the relevant properties like this, therefore the plastic section modulus which we have chosen is 1099.45 centimeter cube, which is almost here and there roughly approximately equal to 1105.2 centimeter cube. Therefore I can proceed with this ISLB 400 at a rate of 56.9. that is what my comment. Therefore, once it is okay, then I'll go with the other relevant checks what we have done in the previous subheadings, right? The first check is the check for the clear spacing between the flanges. S is equal to 800 minus 3 multiplied by width of each of the flange is equal to 165 mm. Between 3 beams only 2 spacings will be there, that divided by 2. It now works out say 152.5, which is greater than 75 mm. Therefore it is okay. The first check is okay. And the second check is as per the class 8.4 page number 59 of IS 800. Just now we have seen that VD is equal to VN is nothing but AVF multiplied by FYW divided by root 3 gamma m naught. Therefore AV is nothing but 400 multiplied by 8 multiplied by FY. Yield stress is equal to 250 divided by 1.1 divided by root 3. That will be 10 to the power 3. It works out say 419.8 kilonewton. However, it is subjected to a factored shear force of 252.9 kilonewton, which is much less than the design shear strength or design shear capacity of 419.8 kilonewton. Therefore, it is okay in the second criteria, shear criteria, right? If it is okay in the second criteria, then what I'll do is now I'll check, is it the check for the high shear, is it a case of the high shear? If it was a case of high shear, then I need to do the remedial measures, right? Therefore, here as per IS 800 2007 class 8.2.1.2 page number 53, right? Here the factored shear force 252.9 is now just greater than right, 0.6 multiplied by VD is equal to 419.8, which is 251.88. However, there is a marginal increase in this value. 252 is just greater than, or I can say that this is approximately 253, this value is equal to 252, hardly 253, it's approximately equal to 252 because just 1 kilonewton more over 250, 1 kilonewton, 1 divided by 250. Therefore, in terms of percentage, it is just 0.5 percentage more. Therefore, this may be neglected. However, this is a case of now high shear. Therefore, for high shear, because this factored shear force is greater than 0.6 VD, this is a case of high shear. However, once it is a case of high shear, then as per this class 9.2.2 page number 70, MD is not MD, it is MDV, where MDV is equal to MD minus beta multiplied by MD minus MFD. It should be less than or equal to 1.2 ZEFI divided by gamma m naught, right? However, here there is no large difference, therefore I am skipping off this. However, if at all you are interested, we have already done this in the previous video. You may just go through the previous video how to calculate the design bending capacity by taking care of this high shear also. Here this is almost here and there the same value, therefore I am not checking in this case, though I need to check even if I check, there is no decrement in the design bending capacity. Therefore, I am skipping off that, right? Where you can check if you are further interested by referring back to the previous video, students, right? Now let us see the section classification as per this table 2 of page number 18 of IS 2007. Therefore, B by thickness of the flange, which is 165 by 2 is the width of the outstanding leg of the flange, that will be 12.5. It now works out to say a value 6.6, which is much less than 9.4, and this stress ratio square root of 250 divided by F by 250 is also 1, and then D by TW, D is H1 is 336.2 divided by thickness of the web, 6 is 42.03, which is much less than 84. Therefore, now I can say that the flange has plastified as well as the web has plastified. Therefore, the section classification indicates the entire section is a plastic section. Therefore, beta B is equal to 1. Therefore, now what I will do is, once beta B is equal to 1, then as per this class 8.2.1.2, page number 53. Now assuming the plastic, now we have already proved that the section is a plastic section, and assuming low shear, just I am assuming that. Therefore, MD is equal to, given by this formula, ZPFI beta B divided by gamma m naught should be less than or equal to 1.2 ZEFI divided by gamma m naught. Beta B is 1 for the plastic section. Therefore, substituting these numeric values, right? 1 multiplied by plastic section modulus is equal to 1099.4 10 to the power 3 multiplied by 250 divided by 1.1. That divided by 10 to the power 6 will work out 249.8 kilonewton meter, right? You should be less than or equal to that 1.2 multiplied by elastic section modulus 465.3 10 to the power 3 multiplied by 250 divided by 1.1 divided by 10 to the power 6. It works out, say, a value 263. However, 249.8 is much less than 263.26. Therefore, I need not modify. Let us say if I get this 289.8, it should be restricted to 263. But I got 249.8, which is less than this upper bound value 263. Therefore, this design bending strength or design bending capacity or flexural resistance or bending resistance is okay. It is okay. Therefore, now let us check for each of the section the bending factor bending moment is equal to 628.5 divided by 3, means each of the section is subjected to 209.4 kilonewton meter only, but the section what you have designed can resist up to 249.8 kilonewton meter. Therefore, the section what you have proposed, this IS just wait for a moment, ISL, not this one, right? This ISLB 400 at a rate of 56.9 is okay in flexure criteria also. It was also okay in shear criteria, right? Once it is okay, then what I'll do is it okay in crippling criteria, right? Also, crippling criteria also. Then as per this class 8.7.4, page number 67, just now you have already seen elaborately, right? Then the bearing width itself is 800 mm, right? Therefore, N2 is equal to 2 multiplied by 2.5 multiplied by H2. Therefore, 2 multiplied by 2.5 multiplied by this H2 is 31.9. Therefore, it now works out, say, a value 159.5. Therefore, the strength of the web against the web buckling FW is equal to B1 plus N2, which is nothing but this 800 plus 159.5 multiplied by 8 multiplied by 250 divided by 1.1 divided by 10 to the power 3. It now works out, say, value 1744.54 kilonewton, which is much more than the shear force to which each of the section is subjected is just 252.9 kilonewton only. Therefore, it is okay from the crippling point of view, right? Now, once it is okay, then is it okay from the web buckling point of view? Therefore, this is the last check for web buckling, right? As per class 8.7.3.1, page number 67, right? However, as per this class 8.2.1.2, page number 53, because this D by TW which is equal to 42.03, which is less than 67, the check for the web buckling need not be done. Already shown in the previous case also, but nevertheless I have shown there. I have shown what that is required, how it need to be done. Now I'll tell at a quicker pace. Therefore, this is in a similar fashion what we have seen in the previous subheading. The slenderness ratio will now work out 2.5 H1 divided by TW. Therefore, upon substitution, 2.5 multiplied by 336.2 divided by 8, say 105 is the slenderness ratio. Therefore, H by TW, H by TF is equal to 400 to 165. 2.42 is much greater than 1.2. Therefore, now as per this table 10 of page number 44 of IS 800 2007, the section is a class A buckling section about the major axis. Therefore, for that, as per this table 9A of page number 40, I am interpolating for lambda is equal to 100, FCD is equal to 132, for lambda is equal to 110, FCD is equal to 115. Therefore, for lambda slenderness ratio 105, the design compressive strength FCD is equal to 123.5 Newton per mm square. Therefore, once I do that, then I'll calculate the web buckling resistance of the section or the buckling load. Buckling load is equal to FCD is equal to B1 plus N1, whereas B1 is equal to 800 plus N1 itself is it is dispersing on either side. You please see, right? It is dispersing on either side like this. Therefore, N1 plus N1, 2N1. However, here N1 is equal to 400 by 2. Therefore, 400 by 2 plus 400 by 2, that works out 400, 800 plus 400, 1200 multiplied by 8, multiplied by 123 divided by 10 power 3. It works out, say, 1185.6 kilonewton. It can resist each of the section, whereas it is subjected to just a factored shear force of 252.9 kilonewton only. Therefore, it is okay. That's why, as per this class itself, we already seen. As per this class 8.2.1.1, page number 53, because D by TW is less than 67, the check for the web buckling need not be done. But nevertheless, I have illustrated, assuming that if all is required, how it should be done. Right? That is how the design of the upper tire, under the second column is now over. Therefore, use 3 ISLB 400. ISLB 400. Now, once we do that, now I'll go for the analysis of the lower tire beams. Then I'll do the designing also, right? Now let me go to the analysis of the lower tire beams, right? Now, this is the third part, student. Second part is also over. First part was the analysis of the and design of the top tire under the concentrated load P1. The second part was the analysis and design of the top tire under the right column. The third part is the analysis and design of the lower tire beams, right? Lower tire beams. Therefore, now I'll do first analysis, then I'll go for the design. Therefore, I'm analyzing the lower tire beams. Actual area A is equal to B multiplied by L1 plus L2 divided by 2. Whereas substituting this, now I'll get 6.2 multiplied by 5.33 plus 2.67 divided by 2, 24.8 meters square. Therefore, now I'll get the safe bearing capacity, means actual soil pressure intensity Q is equal to P1 plus P2 divided by area provided, right? Therefore, that now works out 2500 plus 2000 are the factor loads, that divided by 1.5 divided by 24.8 area provided. Therefore, that works out, say, a value 181.45 divided by 1.5, say 120.97, which is much less than 200 SBC. Therefore, it is okay. Therefore, the factored intensity of the load is equal to 120.97 multiplied by 1.5. Therefore, this what now I'm showing is a factored intensity of the soil pressure 181.45, which will be used for the designs, right? Once it is okay in his check for the safe bearing capacity, then I'll proceed with the analysis, right? Therefore, I already shown how the analysis should be done. The cantilever bending moment under the concentrated load P1 is given by this formula: M1x is equal to Q0 x square divided by 2 L1 minus x by 3 multiplied by L1 minus L2 by B minus P1 by B1 multiplied by x minus A1 prime whole square divided by 2, right? Substituting the numeric values into this, right? Into this, now I'll get M1, right? Under that, first load is equal to 181.45, which is already factored. Intensity of the soil pressure should please make a note, multiplied by x square by 2. L1 is 5.33 minus x by 3 multiplied by 5.33 minus 2.67 divided by 6.2 minus P1 is factored load 2500 divided by B 0.8 that divided by 2 x minus A1 prime. A1 prime is 0.8 whole square. Therefore, that gives this equation as M1x is equal to 90.725 x square multiplied by 5.33 minus 0.143 x minus 1562 multiplied by x minus 6.8 whole square. Therefore, differentiating this with respect to x, now I'll get the shear force under that concentrated load V1x. By equating that to 0, now I'll get V1x to 0. Now I'll get x. By solving that, I am skipping off for amount of time. X is obtained as 1.135 meters. Therefore, now I'll make a check whether is it okay. Yes, it should be greater than 0.8 meter, because this is what, right? This net cantilever projection A1 prime is equal to 0.8 meter. Therefore, it is okay, and it should be less than this 0.8 plus this width B. This width is also 0.8. Therefore, 0.8 plus 0.8 plus this sorry 0.8 plus 0.8 1.6. Therefore, 1.135 is also less than 1.6. Therefore, it is okay. Right? It is okay in this, means not this one, right? Means that section what we have assumed is, which is under this base plate, is okay from lower and upper bound point of view. Lower bound is 0.8 meter and upper bound is 1.6 meter. Therefore, once this x is okay, then the maximum bending moment what will obtain is also okay. Therefore, the maximum bending moment under this concentrated load happening at a distance of 1.135 meter from the left end like this, right? Not this one, right? From this left end of this low tire grillage at a distance of 1.135 meter, right? Is equal to upon substitution 90.725 multiplied by 1.135, because that is x, multiplied by 5.33 minus 0.143 multiplied by 1.135 minus 1562.5 multiplied by 1.131 minus 0.8 whole square. It works out, say, for 28.62 kilonewton meter. Similarly, now this is the cantilever bending moment or negative bending moment, right? Between the two columns, what is the positive bending moments, right? What is the positive bending? Now, the cantilever bending moment will go to the bottom, right? Positive bending moment, then once again cantilever bending moment. That is how the bending moment variation, right? Then I'll find out that positive bending moment or sagging bending moment as by considering a section x at a distance x, right, from the left end, right, here to here, anywhere, right? Therefore, this distance is equal to x, right, x between these two columns. Now this equation is now written, right? This equation is written. Therefore, that is mx is equal to q0 x square divided by 2 L1 minus x by 3 L1 minus L2 divided by 3 minus P1 multiplied by x minus A1. Upon substitution, now I'll get say a value mx is equal to 90.725 x square multiplied by 5.33 minus 0.143 x multiplied by 2500 multiplied by x minus 1.2, because that load under that is equal to 2500, right? Right? Therefore, P1 is already 2500, which is factor load. However, by differentiating this with respect to x, now you get V shear force and equating that to 0. Now I'll get x is equal to 2.93 meter. Now let me check whether is it okay. Yes, it should be greater than 1.6 meter. Yes, it is greater than 1.6 meter because 0.8 plus 0.8, 1.6 meter is the lower bound and the upper bound is 1.6 plus 3.5, 1.6 plus 3.5, which is the 5.1 meter. Yes, it is less than 5.1 meter also. Therefore, it is okay. It is okay, right? Once it is okay, then back substituting this x in the above equation. Now I'll get the positive bending moment. Right? However, I'm showing that as negative because I have considered this with the negative, right? 90.725 multiplied by 2.93 whole square multiplied by 5.33 minus 0.143 multiplied by 2.93 minus 2500 multiplied by 2.93 minus 1.2. I am getting minus 500. Actually, this minus means sagging bending moment. Sagging bending moment, right? Therefore, similarly, now I'll consider a section XX at a distance x. At a distance x from left end, right, below this base plate, therefore here to here, right, here, therefore for that lower bound is this distance, the upper bound is this distance, right. Therefore now I'll check for that lower bound and upper bound later on. If it is okay, then I'll substitute into the general equation of the bending moment. Therefore the cantilever bending moment under the load P2 is given by M3x is equal to Q naught x square by 2 multiplied by L1 minus x by 3 multiplied by L1 minus L2 by 3 minus P1 x minus A1 minus P2 divided by B2, that intensity of the load, minus x minus A1 double prime whole square divided by 2, where A2 double prime whole square divided by 2, where A2 double prime is already calculated as 4.3 meters. Therefore now I'll substitute into this equation so that I'll get M3x is equal to 90.725 x square multiplied by 5.38 minus 0.143x minus 2500 multiplied by x minus 1.2 minus 1250 multiplied by x minus 4.3 whole square. However, once I get this bending moment, now I'll differentiate with respect to x so that I'll get the shear force V3x, and if I equate that to 0, now I'll get x is equal to 4.8 meter. That is greater than 4.7 meter and it is less than 6.2 meter. It is okay. Therefore, once it is okay in lower bound and upper bound checks, then what I'll do, 4.8 is greater than 4.7 meter, it is okay, and less than 6.2 meter. Therefore, once it is okay, then I'll substitute this in the above equation. Therefore, the maximum bending moment under that second concentrated load is equal to 90.725 multiplied by 4.8 whole square multiplied by 5.33 minus 0.143 multiplied by 4.8 minus 2500 multiplied by 4.8 minus 1.2 minus 1200 multiplied by 4.8 minus 4.3 whole square. That works out say 394 kilonewton meter. Therefore now I can check that out of this M1, M12 and M3 means 394 is one value, another value positive bending moment means sagging bending moment is 500, hogging bending moment is 1, result is 394, another result just below the first concentrated load is 428. Therefore out of all these 428 negative bending moment is less than that of the sagging bending moment 500. Therefore that will govern the design. Therefore I have the three results. Therefore out of all these, right, 394 is not governing the design, nor that of the 428.62 just below that concentrated load, cantilever bending moment 428 will not govern, but in between these two columns 500 kilonewton is governing. Therefore that is my governing bending moment. Therefore that is what design bending moment. Once I get the design bending moment, then I'll go for the design of the section. Therefore next subheading is the design of the lower tier beams, for which now I need to do the first subheading as a trial section as per class 8.2.1.2 of IS 800 2007, page number 53. Assuming the section as a plastic section and low shear, the plastic section model is required is equal to factored bending moment 500 divided by Fy is equal to 250 divided by 1.1, that is equal to 2200 10 to the power 3 mm cube. However, in the lower tire we can assume many number of beams like this, many number of beams. Therefore, this is my assumption that assuming because the length available is equal to 2.67 meter, then what now I'll say that assuming a clear spacing of 75 mm, how many number of beams I can provide, right? Assuming BF is equal to 100 mm, right? Width of the each of the flange as 100 mm. This is my assumption, right? Therefore, now I'll say that is equal to n multiplied by BF plus between n beams, n minus 1 spacings will be there with a spacing of 75 mm. This is my assumption. Is equal to 2670. Solving this, now I'll get at maximum 15.7 beams can be assumed. Therefore, R say 15 beams. Therefore, the section, assuming 15 number of beams, the section modulus, plastic section modulus required is equal to that value what we obtained, 2200 into 10 to the power 3 divided by 15. It works out approximately 147 into 10 to the power 3 mm cube. Therefore, once I require this, now we increase by this 20%. Therefore, 1.2 multiplied by that value. Therefore, now I'll get this result as this already if I have 1.2 multiplied by 2000 divided by this 15 is equal to 160 student, right? Therefore, if I multiply this 146.6 with 1.2, I'll get approximately 160 into 10 to the power 3 mm cube. Therefore, once I fix the plastic section modulus for the trial section, now I'll try with a section from IS 800 2007 table 46 page number 139, or alternatively from SP 61 page number 2 table 1. Then I'll try with ISLB 200 at a rate of 19.8 kg per meter. Let me go to that page. ISLB 200 from this page 139. Let me go to the page number 139, students, right? Yes, and then ISLB 200, or this one, ISLB 200. Yes, ISLB 200 at a rate of 19.8, which is furnishing a plastic section modulus of 184.34. Therefore, even I'll note down the other relevant properties. Therefore, I'm noting down all the relevant properties, right? It is furnishing a plastic section modulus of 184.34 10 to the power 3 mm cube, which is just greater than the trial section modulus. What I need to fix is just 160. Therefore, it is okay. Therefore, the other relevant properties are like this, that the elastic section modulus is equal to 169.7 10 to the power 3 mm cube. Depth of the section H is equal to 2000, and breadth of the flange 100. Thickness of the 5.4, and H2 is equal to 17.15, and H1 is equal to 165.7 mm. Therefore, now I'll do once again all the relevant checks. Once I fix a trial section, all those checks what you have done previously in the 2 times you have done these checks, right? Therefore, now I'll initiate a few of the checks. I'll skip off. The first check is the check for the clear spacing between the ends of the flanges is equal to 2670 mm is already available, between which I am providing 15 beams with a width of the flange 100 mm. Therefore, now 1500 is the last. Therefore, 1610 divided by 14. That now works out say 83.6, which is greater than 75 mm. Therefore, it is okay. Also, right, once this is okay, at the other end where just 2670 mm is available. Let me go to this schematic, student, right? At the other end just 2670 is only available. There I have made a check, whereas at this end more length is available, L1 is more. Therefore, there even you need not check. you need not check. But nevertheless, if I do that check, how it is, right? Therefore, at this end, 5320 space is available, from which if I deduct 15 100s, that divided by 14, it works out 273.6, which is much greater than 75 mm. Therefore, at this other end, right, the gap is more, whereas the moment you go to the other side, they are just narrowing down like this, just narrowing down. Whereas at the other end, the space is more. Whereas coming to the top, the right end, they are narrowing down like this, right? Narrowing down. The space is narrowing down, right? Therefore, that is how the space is narrowing down like this, right? The space is narrowing down like this. Whereas at the other end, more space is there, right? At the other end, these are narrowing down, right? Like this. Okay. Therefore, once this is okay, then this is okay in the check for the spacing. Therefore, I think other checks I'll skip off, right? Because I have done in the same problem 2 times, right? Check for the shear, right? Check for high shear. Second, check for bending strength, and check for web crippling, check for web buckling. Therefore, all those checks you can do. I am sure that this will not fail because I am using more number of beams. 50 number of beams are there, right? Therefore, similarly, you can do those all checks, and finally, you can satisfy on your own that they are also satisfied thoroughly. I am skipping off for want of time because I already done this 2 times in today's problem itself. Therefore, I don't want to do for the 3rd time, right? Therefore, finally, it is once this is okay, then I am drawing that section. Therefore, this is under the first load 3 ISLB 550, right? Or the width of the base plate 800 mm by 800 mm like this, right? This is a 800 mm by 800 mm, right? Throwing the loads on the ISLB 550, right? Similarly, these are the beams under the second load. Even this base plate is also 800 by 800, but now just now we have designed, right? I think ISLB 400 is the section what we have fixed, right? 3 beams were fixed. However, just now we have fixed the section for the lower tier beams as ISLB 200 at a rate of 19.8, right? These are those beams, right? These are the three beams under the left column and right column, but this is the low tier beams ISLB 200 below the first tier of the first as well as the second column like this, right? Therefore, there is the first beam, second beam, so on and so forth. Last one is 15 beam. Now you can see that here the gap between these 2 ends is more when compared to that of the gap between these 2, right? Where the length L2 is equal to 2670 only, whereas at the other end, right, this length is equal to 5330 from this end of the grillage beam to the end of the grillage beam. Whereas for the footing, we need to add 100 mm here plus 100 mm here. Therefore, the length at the other end is equal to 5530. At the other end, it is 2870, and the width is equal to 6200 plus 200, right? 6400. This is the width. Therefore, this is how in plan as well as in sectional elevation. This is what the first, right, concrete pour, which is 750 mm because this is 200 mm. Therefore, now I'll assume 100 mm here, right? This is 100 mm. I'll assume, right? Therefore, the concrete, right, first pour is 300 mm, right? Whereas here we do have this 550 is the pedestal, right? 550 plus 100 mm, 650, right? Pedestal will be there. Here also similarly 400 plus 100 mm, that pedestal will be there, over which the base plate will be supported, right? That is how even you can put the pedestals like this, or even you can show like this. If you want to optimize, you can put the pedestals, and this is one concrete through and through, one pour, right? That is how the schematic student. I hope you enjoyed the discussions what we had in today's class, right? Of the combined trapezoidal grillage foundation, right? In the next class, we shall see the designs of the other steel structural designs as per the limit state method, right? Then, if you have enjoyed the discussions, don't forget to click like, share, subscribe to our YouTube channel and support our YouTube channel, right? Till then, bye bye.